So, just like in your first semester of calculus, you started off with, after limits, you learned some various derivative recipes, and then you went to applications, right? You wanted to figure out, optimization, how to find relative extrema. It, and you can kind of see the same path, right? We're pretty much progressing the same way. We've learned how to do some partial derivatives. Um, we've worked on some various ways that you would do partial derivatives, based on chain rules and things of this nature. And then, we've started to progress into doing application work with derivatives, right? So now we are kind of at that section of optimization. We're at that section where we're trying to find minimums. This is one of those sections that you're just going to have to dig in to the practice problems so that you can because I'm going to do a problem for you. But to be honest, I mean, no matter, if I do 2 of them, if I do 3 of them, 4 of them, unless you have dug into the practice problems, you still may end up seeing a problem that doesn't exactly resemble right the one that I covered in the lecture. So how do you prepare? Well, you have to prepare by getting exposure. And how do you get exposure? You get exposure by rolling your sleeves up and trying some different problems. That's the only way, right? Make some mistakes when the stakes are low, when you can find your mistakes and you don't have to get a bad grade on a test. But I'm gonna do one optimization problem. Not that it's going to be easy, and not that it's going to be quick, but let me begin. So your company, let's say, is going to construct some type of water line, and it's going to, you can imagine, I don't know, maybe you're on the Potomac River or something like that. So you have the idea is to connect some water line from point P to point S. Now, what you can imagine is that, depending on the depth of water and so forth, that there are going to be various construction costs at different locations, right? So what we're going to assume is that within this region right here, right, so you could go from point P. If you stopped here, that's going to be point Q. If you went from just imagine that point Q can be anywhere in this region, right? But wherever it is, anything in this region costs, construction costs of $3,000 per kilometer. So must pass through regions where construction costs differ. And let's start with the first. So the cost per kilometer in dollars is $3,000 from in the region P to Q. So anything in here. So let's try to start building some information here. So that the length of P to Q is going to be $3,000 per kilometer. All right. So we have arbitrarily just put Q here. So P to Q. All right. Now, once you are at Q, you're going to incur a different set of construction costs over the next region. So wherever you land here in this region, anything in this region here, any construction is going to be $2,000 per kilometer. So, well, you have to you have to go through this region, so, and you have to stop somewhere. We'll call this point where you stop R. Right, so again, R can be anywhere here. So the length of P to R, my apologies, not P to R, you've already gone through P. You're at Q now, right? So the length from Q to R, well, that's going to be $2,000 per kilometer. Finally, once you have reached R, you're basically on land, I believe. Let me continue reading. So 2,000 from Q to R, and K, or $1,000 from R to S. So once you've reached here, you can then operate wherever you land. You can operate from there to the point S, and it's going to be $1,000 per kilometer. So R to S equals $1,000 per kilometer. Okay, well, the idea is you are, what we want to do is we want to find what the minimum costs, or what, the minimum cost could be. Because in other words, your company doesn't care if you run, directly from point P to S. Your company doesn't care if you go straight to land and then over to S. Your company doesn't care. It's trying to what? It's trying to minimize costs. So I'm going to show you a better picture of this on the next page. And this is the figure that came with the problem. I just wanted to jot it down from here to here. I figured it'd be better to do it this way. So this is the actual picture, and you can kind of see what we have. So based on the information that we're given, so again, imagine you're given this picture. We know that you have 2 kilometers of distance in the $3,000 construction cost zone. You got 1 kilometer of distance in the $2,000 construction zone, and we know that any construction on land is going to be $1,000 per kilometer. Well, it should make sense that obviously we're not given a cost function, right? This is more like the real world. Your company wants to minimize costs, but they don't give you a cost function. It's your job to build one. Then your job to use your mathematical skills to optimize it. We got to build a cost function. Well, based on everything we have, everything we know, cost is just distance multiplied by the price per kilometer, right? So we need to start by building distance. All right. So let's go back to this picture, because this picture tells us a lot of the information. So we have 10 kilometers from point P to point S is 10 kilometers. We also have 3 kilometers from basically starting from point P to land. Now, since you don't know yet, right? You don't know yet where you're going to, how you're going to run from point P through the first region. You don't know where you're going to land, in other words, right? We're going to say that let's let X represent the distance to point Q. So again, if your point Q was here, then again your X is the distance. And you can see that you're basically forming right triangles here, right? You can see that the right triangle is being formed. Okay, so let's see if we can capture P to Q. All right, well, you can see that P to Q is the hypotenuse of the right triangle that I'm drawing. Now, one of the sides is 2 kilometers. The other side is what x, because we don't know where we're going to stop. So if you want to just simply use Pythagorean theorem, you can write P to Q as a function of x. So that's just going to be what? That's just going to be the square root of each side squared. So that's x squared plus 2 squared, which is 4. All right, now, stay with me here. So once you are at point Q, we now have to think about, you're now going to be traveling through, you're going to be building another triangle, right? But you have to think about how do we adjust how do we come up with the sides of this second right triangle? This is a harder one for some students to see. So I mean, we know that the hypotenuse is the segment from Q to R. Now it's fairly easy to see that one side of your right triangle is just the length or the distance of 1 kilometer, right? So we know that this side here is 1. But the question that I have for you is, how do you build this side? Interesting. Well, let me write it, and then let's reflect. So Q to R segment, let me see if you agree with it. This side is going to be y minus x. Y minus x. So that hypotenuse would be the square root of y minus x squared plus 1 squared, which is just 1. But let's go back, let's reflect on that, because the ability to model is an extremely important ability, right? So you have to think about y is going to be the distance from here to here. But you can't just use y, because no, my sincere apologies. You have to think about the distance y, which is from here to here. I said everything I said is perfect. The distance y minus the distance that you traveled before at x would give you the distance that you want. So that's why it's y minus x. So y minus x, and of course that would be squared once you put it into your Pythagorean theorem. Now, once you're here, right? Once you're here on land, well, this is quite simple. You just need to know how much farther do I need to go to get to point S. Well, it's possible that you just went straight south and landed here. In that case, it would be 10 kilometers, right? But it's going to be 10, the most it could be is 10, but it's going to be 10 minus something. Well, it's going to be 10 minus however long of a distance y is. So 10 minus y will give us the rest of the distance that we need to travel. All right. So, cost, right? That's the idea. So cost, total cost is going to be equal to what? It's going to be equal to cost per kilometer multiplied by the number of kilometers you traveled. So does it make sense that this is the length, the number of kilometers that you traveled. This is the number of kilometers you traveled. This is the number of kilometers you traveled. And we know that this is 3,000 per kilometer, plus this is 2,000 per kilometer, this is 1,000 per kilometer. So when I plug everything in, we end up with C, right? And this ends up being C of x, y is going to be equal to 3,000 times, that's the cost per kilometer, times that distance, which is square root of x squared plus 4, plus 2,000 times the square root of y minus x squared plus 1. Let's go ahead and, as I'm running out of space here, see if I can make this a little bit smaller. I didn't have to make it that small. All right, that's okay. Plus, and then you have 1,000 per kilometer, and that would be times the distance that you traveled, 10 minus y. All right, so this is your cost function, and it's a function of the distance x, the distance y. So I'm going to let you kind of chew on this for a second, and we'll take a break. Let me kind of tell you where we're going to go in the next video. So I'm going to grab this cost function and think back to Calc 1. Remember, in optimization problems, what did you do? You took the derivative. You set the derivative equal to 0. So that is exactly what I'm going to do. I'm going to take the partial derivatives of this with respect to x, then the partial derivative with respect to y, and I'm going to set it equal. I'm going to set them equal to 0. So you want to get back.